All right, guys. So this is going to be our second video, kind of going over uh, like some practice problems where a rice chart might help you organize some things, and also kind of looking into this video, or what we're going to be looking at is some simplifications we can make. So sometimes you might be doing this equilibrium problem where you're trying to solve for something, and the way you have it set up, the only way you can solve for it is by solve for x. So you set up an equation and you're solving for x, but the only way you're going to solve for it is graphing to solve for x. So some algebra 2 skills. However, on the AP exam, anytime you would come across this type of scenario, there would always be a simplification. So I'm going to show you, what it would look like if you didn't simplify it, and then how you would simplify it and why you're allowed to simplify it, and then show you how this question might actually show up on the actual AP exam. So the practice we're doing is coming from one of the free response questions from the 2016 exam, and initially the way I'm going to go through the problem isn't what they asked, but then I'll show you what they asked. And really, what this is going to tie into is next unit, Unit 5, when we get into weak acids and weak bases and them at equilibrium, and calculating the pHs of a weak acid solution or a weak base solution. But right now, we can still do it, even though we haven't gotten to Unit 5. It's really just an equilibrium problem and knowing a few definitions. So let's go ahead and jump into this one. Okay. So again, this is about, making rice charts, and also kind of understanding when you can simplify an expression so that it makes it easier to solve for x versus graphing. Okay. So when we first go through this problem, what we're going to end up getting to a point is where if we're going to want to figure out what x is, we're going to have to graph to solve it, unless we make a simplification. And a thing I want you to understand is, if you really understand the concepts and you're setting up these problems using rice charts and that kind of thing, whether it be an acid base question or a solubility product, which is KSP question or something, you're always going to be able to make a simplification on the actual exam where you so that you don't have to graph to solve for x. I've never seen it on the AP exam where you have to graph to solve for x. You can always make the simplification, and I'll show you what I mean later. Okay, so let's look at this problem. All right, so we're given this reaction. All right, so we have this compound, this molecule, aqueous, is in water, and it's reacting with water and becoming this ion and that ion. So really, what's going on is this is a Bronsted-Lowry acid-base reaction. It's also an Arrhenius acid reaction, because this is bumping into water. It's this hydrogen is being added to the water, and so this becomes an anion because it lost an H plus, and the water turns into hydronium. And so the reason why this is an acid reaction is because it's producing hydronium in water. But that really doesn't matter right now. They give us the equation, and they give us the equilibrium constant for the equation. Now, and it's 10 raised to the negative 10th power. The reason why they're calling it Ka is because this is the particular type of reaction that shows an acid acting like an acid in water. So the K for this reaction is called a Ka. Now, they could give you this equation and just say K equals, and it would be the same value. It's just understood that this would be the Ka for this weak acid, because this reaction is showing that weak acid acting like an acid with water. Okay, so that's the whole idea. All right. And so the first thing I want us to do is just write the equilibrium expression for this K value. Okay, so we would just do products over reactants, coefficients become exponents. All the coefficients are 1, so we don't have to worry about that. But remember, don't use liquids or solids, so we wouldn't include water in the expression. So all we would have to do is say Ka equals, and again, it would be this in brackets times this in brackets over that in brackets, right? So C6H5O minus times the hydronium concentration over this acid's concentration. And now remember, so we know what this expression is equal to. It's equal to the Ka, and we know what Ka equals to. So if you want to, you could just say this number, put that in for Ka. So that number, 1.12 times 10 to the negative 10 equals this expression. And remember, I didn't include them here, but it would be equal to this concentration at equilibrium times this concentration at equilibrium times this concentration. So remember, a lot of times we'll put a little subscript EQ there to remind us that we need our equilibrium concentrations. Okay? But again, not including water. All right. So now we're given more information. We have the concentration of the acid, C6H5OH. So we have the concentration of this initially. Okay? And the goal is, so it's 0.75 molar initially, not at equilibrium, okay? And our goal is to figure out, well, based on the equilibrium position of the reaction, which is the K, based on that, what will the equilibrium concentration of H3O plus be? What will the concentration of hydronium be at equilibrium? So this would be a good idea to set up a Rice chart. So let's kind of organize what we have. All right, so we have our reaction. Notice I'm just kind of putting dashes through the water because we don't care. If something's a liquid or a solid, you can put it at the top in your Rice chart, but you're not going to put any numbers for it. All right. So our initial molarity of C6H5OH is 0.75, but if this reaction doesn't occur, our initial concentration is C6H5 of C6H5O minus is 0, and our amount of hydronium is 0. Now, really, our amount of hydronium, because this is happening in water, is really 1 times 10 to the negative 7 to start with, but that's a lot smaller compared to that, so we're just going to call it 0. All right. So, in order to reach equilibrium, the reaction has to shift this way towards the products because in order to be at equilibrium, we have to have some of everything. We have to have some of everything. And right now, we only have some of that. We don't have any of our products. So if it's going to shift this way to reach equilibrium, we're going to lose this, and we're going to gain that. Okay? So it's going to be minus x over here and plus x and plus x. And we don't have to worry about any coefficients. But remember, like if the coefficient of this were 2, this would be plus 2x. If the coefficient over here was like 3, then it would be minus 3x. All right, but everything's 1, so we're good to go. All right, so then at equilibrium, the concentration of the acid is going to be 0.75 minus x. The concentration of this anion is going to be x, and the concentration of hydronium is going to be x. All right, so what we're doing here is we're getting our equilibrium concentrations of everything in the reaction in terms of x. That's one thing you can do in a Rice chart. Get your equilibriums in terms of x. And now your goal is solve for x. And if I solve for x, that is going to be the answer to the original question because x in our Rice chart is representing the equilibrium molarity of hydronium, right? Which is what this question is asking about. All right. So what we're going to do is we're going to plug our equilibrium concentrations in terms of x into our equilibrium expression and set it equal to K because we know what this value is. We know what Ka actually is. So this is our equilibrium expression. I'm going to plug in our value of Ka over here. According to our Rice chart, the concentration of C6H5O minus is X. The concentration of hydronium is X. And the concentration of our reactant is 0.75 minus X. So this is what we got. All right. So the Ka value equals X times X over 0.75 minus X. Okay. And so we've been through Algebra 2. So we should be able to solve for x, but maybe we forgot. All right, but let's understand what we would do is use our graphing calculator, and we would graph to solve for x. All right, so now I'm going to just simplify the expression a little bit. And so this is my expression. I got to solve for x, right? So x times x is x squared 0.75 minus x is on the bottom. And that 0.775 minus x is together. So, put it in parentheses because, if we were going to cross multiply here, it would be that time. We'd have to, distribute that through the entire thing there. All right. But anyway, eventually we're not going to have to do that. But if we were to graph to solve for x here, I would go to my y equals screen on my graphing calculator. I'd put y equals this number in y1, and I'd put this expression in y2. And I'd hit graph, and then what you're trying to do is you're trying to find the y-intercepts of this, the x-intercepts. Yeah, the x-intercepts of this horizontal line. Okay, that would be at y1, all right? So we'll practice that in class a little bit, but again, eventually, any test, any quiz, any AP classroom questions, final exam, AP exam, if you got to this point, there's a way to simplify this expression so you don't have to graph, and I'm going to show you how to do that in a second. And I'm going to show you that when we do simplify it, it ends up being the same number, all right? So if we were to graph to solve for x, this is what we would get, and I rounded my answer to 3 sig figs here. So graphing to solve for x, I get 9.17 times 10 to the negative 6. Okay, and so remember that would be our answer to this question, and our units would be moles per liter or capital M because X is representing the molar concentration of the hydronium at equilibrium. So our answer is this, right? I graph to solve for X. That's our answer, but we'd have to include units. We would say capital M or moles per liter, okay? But let's talk about how we can simplify it, okay? So let's understand something about what this value of Ka represents, right? That's a really small number. That's a lot less than 1, right? That's a lot more less than 1 than 0.75 is, okay? So yes, the reaction has to shift this way to reach equilibrium because we don't have any of these two things. But it doesn't have to shift a lot. It doesn't have to shift a lot. It's going to be really small, right? I don't need a lot of this to reach equilibrium because this equilibrium constant is telling me that when equilibrium is established, you have a lot more reactant than product. So the concentration of this at equilibrium is going to be much higher than the concentrations of these at equilibrium. So what does that tell you about X? It tells you that X is going to be a really small number, right? So this is going to lose X, right? 0.75 minus X, we're going to lose X, but X is going to be so small to compared to 0.75 that when I do 0.75 minus whatever X comes out to be, the answer to that is going to be pretty much 0.75, right? It's like when I go to the doctor and I'm, weighing myself and I look at the number and I go, wait a minute, let me take off my shirt. It's like, yeah, taking off my shirt really doesn't change the number, right? I lost the mass of my shirt, but I'm still basically the number that originally appeared, right? So yeah, the 0.75 is going to lose X, but X is pretty much nothing compared to the 0.75, okay? So what we're going to do is say 0.75 minus X, which is our concentration of the reactant at equilibrium, we're going to say that's pretty much 0.75. So we're going to write our expression the kind of the same way we did, but we're going to get rid of this minus X part. We're going to get rid of that because essentially the concentration of the original acid at equilibrium is just 0.75. So we're just going to use its initial concentration as its equilibrium concentration because it's pretty much the same thing. Okay, we call this the 5% rule. And basically what it says is if X is less than 5% of what you're subtracting it from, or you might be in a situation where you're adding X to a number, but if X is less than 5% of what you're subtracting it from or adding it to, you are allowed to just get rid of that and just use the original value. All right, and so that's what we're going to be doing. So instead of graphing to solve for x and wasting some time, valuable time that we have on the AP exam, we're just going to say this expression. Okay? And so now all I have to do is cross multiply and take the square root to solve for x. Now, what I want you to notice is when we do that, we get the same exact answer. If I do this 0.75 times the Ka value, and then I take the square root of it, I end up with the same answer I got from when I graphed to solve for x. And that's because, especially when you're rounding to the proper number of sig digs, if you're using the 5% rule to simplify your expression, you're going to end up with the same number. Whether you chose to simplify or you chose to graph, you're going to end up with the same number. Now, you get a graphing calculator. You can use a graphing calculator. You don't get one. You have to bring your own calculator for the AP exam. But you get to use it on both sections. So you could always graph it, but you're going to be able to make this simplification. Okay? So we answered the question. And whether or not we graphed to solve for x, or made that simplification, made the 5% rule simplification, we ended up with the same number. So the equilibrium concentration of hydronium in that process was 9.2 times 10 to the negative 6 moles per liter. Okay. Now, I'm going to take this a little bit forward and show you what you're going to be getting into in Unit 5. Okay, so this is where I got the idea for this question, is from this AP exam. Again, this was from 2016. So notice they give us that same reaction, right? So we got this same reaction. They give us the Ka value. But notice the first question is just, hey, what's the pH of a 0.75 molar solution of this acid? Okay, so whenever you have a weak acid in solution, I'm going to tell you to use your Ka shortcut, but the Ka shortcut is derived from making a Rice chart for a weak acid reaction and simplifying it so you don't have to graph. So exactly what we just did, and I'll show you what I mean. But remember, let's recall, we've been over what pH is. Remember, pH is the negative logarithm of the hydronium concentration. So in order to answer this question, we have to figure out the hydronium ion concentration of this reaction at equilibrium. And then once we do, we take the negative log of that to get the pH. So essentially, to answer this question, we have to do exactly what we just did in that previous practice problem. We have to calculate the equilibrium concentration of the hydronium ion, okay? And then once we have it, we'll take the negative log of it to get the pH, okay? So it would be, I did my simplification, I solve for x, knowing that x is the hydronium concentration, and then to get to pH, I just take the negative log of the hydronium concentration, and that gives me the pH. So that would be the pH of this solution. And that's more of a Unit 5 question. We'll get there. But, I mean, it's pretty, it's just equilibrium when it comes down to it. All right. So moving forward, once we get to Unit 5, we're going to learn the Ka shortcut. And so if you have a weak acid and that's all you've put in your solution, sometimes we get into other scenarios where we might add some other stuff and it gets a little more complicated. But if all you have is a weak acid in solution, you can jump to this shortcut where you say Ka equals x squared over the initial concentration of the acid minus x. But remember, we're going to simplify that. We're going to get rid of that minus x. We're going to 5% rule it. And so our Ka shortcut is always this. Whenever we have a weak acid in solution, we can say Ka equals x squared over the initial concentration of the acid, knowing that in this shortcut, if I can solve for x, x is the hydronium concentration, and the negative log of x would be equal to the pH. And that's what we could have done real quick for this question. You go, oh, that's a weak acid in solution. I want the pH. So what I do, I use this shortcut, plug in 0.75, plug in the Ka value, solve for x. And if I take the negative log of x, that'll be the pH, because x in this shortcut represents the hydronium concentration. It would also represent the A minus concentration. So if we go back to our reaction, I guess I should just go to this one. If we go back to our reaction, if you're calling your acid HA, then this is A minus, okay? And then that would be H3O plus, right? Okay, so anyway. But we'll work on all that in Unit 5 when we get to acid-base stuff. But the main thing is just, seeing, another use for our rice chart, and also kind of understanding that if you're ever in a situation where you think, oh, well, the only way I can answer this question is by graphing to solve for X, think about it a little bit more and go, wait a minute, is there a way I can simplify this so that I don't have to graph to solve for X? And start looking at what the Ka value means and what that, or the K value means and what that means in terms of the change that's actually happening in your rice chart. Is that minus X or is that plus X? Is that X going to be really small? So adding X to a number really isn't going to do much, or subtracting X from a number really isn't going to do much. So it's that kind of thing. All right. So hopefully that continues to help with your understanding of, equilibrium, rice charts, and all that. And then, there's going to be a new video coming out here soon that's going to be more rice chart stuff, but also this thing called doing a Q calculation. All right. And what Q is compared to K. All right. So capital Q, not lowercase q, not heat from last unit, but capital Q, which is a different thing, which we'll get into in the next video. All right, so hope you're having a good one.